Hello, this is a video about the evaluation of resistivity anomalies in CSEM data. As you probably know, CSEM is a technology that allows us to predict resistivity in the subsurface, like this one that's overlaid on seismic, by putting some voltmeters on the seabed and towing an antenna that generates an electromagnetic signal out here. And the propagation of that electromagnetic signal being captured in the receivers allows us to reconstruct the resistivity field in the subsurface. Like so many other geophysical technologies, CSEM relies sometimes in the presence of anomalies, like this one here. That's why we take it very seriously to have good criteria to define whether we have or don't have a CSEM anomaly, or there is an anomaly in the resistivity information. I'm going to illustrate the importance of having these criteria available using an example from the Southern North Sea. There is a longer video that explains in detail that case, a link to that one in the description of the video below. So let's go straight to it. In the dataset that I'm describing from the Southern North Sea, in the seismic you have quite a few distinctive structures that contain seismic amplitude anomalies, like that one, or that one, here, and here. They all contain bright spots on top and flat spots underneath, and they all sit on highs. Now if we look at the matching CSEM resistivity response that is processed in a completely independent way, this is what we obtain. So you can see that some of these seismic amplitude anomalies contain matching resistivity anomaly, like here. Yeah. If we look at this on a map view, first on the seismic, we see this. These are negative amplitude anomalies that match structure, like that one. And if we do the same on resistivity, rather than doing a seismic amplitude extraction or an amplitude extraction along the horizon, as we do on seismic, on CSEM, for reasons that will be clear later, what we do is we take a window average around the top of the reservoir, take a window around it, and calculate the average resistivity on the CSEM data. And this is what we obtain. So you can see that there are clear resistivity anomalies, like here on the right, and there are less clear resistivity anomalies, like this one. What you're looking at is a map of average resistivity provided by CSEM. But what does that average resistivity mean? That average resistivity means if I drilled a well and obtained this well log, which is of course a very simplified earth, you have here a background resistivity out here, and then you have a resistivity anomaly at the log scale, so very high resolution here. If I acquired CSEM data over this same location and created an inversion, this is what the inversion would produce. It would essentially produce the same background, a matching background, and then you would get an increased value around where the actual resistor sits, and the CSEM will recover something that's thicker and lower magnitude than the high resolution version. But what's interesting is that if you take what's called the transfer resistance equivalence applies, it means if you take a window like this one that encompasses the whole CSEM anomaly and you calculate the average resistivity on the log, that should match the average resistivity of the CSEM. So the CSEM is giving you at any given point an estimation of the average resistivity that you will encounter if you drill a well there in a certain window, and the window width is determined by the CSEM resolution. So when can we say we see something that's anomalous versus something where there is no anomaly? So I'm going to take two pieces of the previous map that I showed, and I'm going to show them independently here with two different color scales, which is the key. Here on the left you see a CSEM anomaly, here on the right you see another CSEM anomaly. The horizontal scales are fairly similar, so you can see that the CSEM anomaly on the right is actually larger than the one on the left, as the map shows it. As we've shown before, each one of these points is giving you an estimation of the average resistivity that will be encountered if you drilled a well there. So one of the things that we like doing is take one of the maps, like this one, and make a histogram of the values in that map. So you can observe here there is a large lobe with high probability of relatively low values, and then there is a long tail of high values to the right. And that's what an anomaly is. This is essentially the definition of an anomaly. You have high probability of relatively low values, they are actually fairly normally distributed, and then you have something that much higher values that are very unlikely to be essentially just noise from the background. Yeah. Now, in order to calculate where my anomaly starts, so somewhere in between here, my anomaly will start. Now, where? That's the key question. So in order to do that, first thing we need to do is we need to fit a background distribution to my large probability lobe here. And here you have the one that I fit, which is essentially a normal distribution with a P90 of 2.24 meters and a P10 of 2.44. So this P10, P90 distance is a common occurrence, being around 10% of the value of the resistivity that you're measuring. In this case, it's a bit smaller. It's a sort of good rule of thumb. Now, if my background goes from 2.24 to a P10 of 2.44, numbers above 2.44 have a probability of belonging to the background that's below 10%. So 90% chance that stuff above 2.44 does not belong to the background. And there you have to choose exactly where you want your boundaries to be. Somewhere higher than that, maybe you want to choose 20% of probability belonging to the background. My experience is that I like probabilities to be fairly low, and I tend to choose these two values that are written down here. My low confidence bit being 0.5% probability of belonging to the background, and a very high confidence point that is 0.005% of belonging to the background. The thing is, it's very easy to use the distance of P10 and P90 to actually put those two numbers in there, and you just have to take the P10, P90 distance and just add half the distance to the P10. That brings you to 0.5% probability here. 2.54 meters is 0.5% probability that any value above that belongs to the background. And if you take another half distance of the P10, P90 of the background, then that brings you up to 0.005%. So this is super high confidence stuff out here. This is lower confidence. Yeah, but you're free to choose whatever values you are comfortable with. Of course, what I can do is I can take these two values, my P90 of the cutoff and my P10 of the cutoff, so my low confidence and my high confidence anomaly boundaries, and I can project them onto the map. One of the things I like is I like to tune my color scale so that the low end of the color scale is the P90 of the background and the high end of the color scales is the P10 of the cutoff. So that gives you a good idea of the background distribution. You can see there is some noise in this background. It's going up and down a bit. And then it gives you, it becomes dark red, where 99.995% likely that this stuff that's dark red, that does not belong to the background. Okay, so there's a very high confidence, there's a relatively large, pretty sharp, high confidence anomaly here. There is something that does not belong to the background here in this plot. Now let's go to the other one and do the same. So this was my original average resistivity map. Let's take the histogram. Now you can right away see there is a very stark difference in the histogram. This histogram is much narrower than the previous one. There is no obvious tail. Of course, you can always put your background in a way that you might get some red, but it's very difficult to identify a very long tail within this background. Yeah, it's much narrower. And if you think about the rule that we used before, which is the width of the background is very often around the P90 to P10 distance is very often around 10% of the average value. We can use that in order to build the background here. And one thing that we like is we like to match the mode with the mode of the histogram. So we don't like our mode to stray very far from the histogram mode here. So I could actually make a background down here, that would mean my mode would be pretty far away from the histogram mode. So if I wanted to do sort of an optimistic interpretation here, I would bring my mode down to here, and this would be my background distributions and my cutoff distribution with correspondingly using exactly the same probability criteria as I used before, but this would be my numbers. And actually, if I take the same as before, the P90 cutoff value and the P10 cutoff value and project them as contours in the map, what I get is that outline out here, a light gray outline. There's no black outline, meaning there are absolutely no values where I have high confidence with the interpretation that I've made that there is an anomaly here. So you can see even the low confidence is actually pretty small and the high confidence is simply non-existent. And this is why it's really important to look at your values rather than just play with your color scale, because it's very easy to fool yourself using a color scale. It's much harder to do that when you look at values. So this would be our original couple of maps that we had with no reference to any background or any cutoffs. And if we do the same, meaning we put the same color scales in both of them, tying the low end of the color scale to the P90 of the background and the high end of the color scale to the P10 of the cutoff distribution, then we obtain this. So this would be statistically equivalent maps. You can see very clear anomaly on the left, fairly large, high confidence anomaly on the left. Here, almost no anomaly and only low confidence anomaly, and a very small one at that on the right. So it's really important to have criteria such as the ones that we've just shown, because you can actually fool yourself playing with colors. Thank you very much for your attention. Hope you enjoyed that.